Hello everyone. In this video we are going to talk about a problem on basic theory of functions. Okay, this problem came in West Bengal PSC 2022. This exam was for recruitment of assistant professors. But anyway, this problem is extremely important, I feel so, for the other competitive math exams also, because this problem is really tricky to my opinion. So if you like the content of this video, kindly take a moment to like this video and of course subscribe our channel. Well, so in the problem, a function f is given to you whose domain is 0, 1, open interval, this is important, and the codomain is full of the real numbers r. Okay, the expression of the function is also given. So fx is 2x minus 1 over x into 1 over x, 1 minus x. Okay, you have to check whether the function is 1 1 or on 2. So basically just check whether it is 1 1 or on 2. Well, so to check whether it is 1 1, people consider f dash x, right? F dash x. But here f dash x calculation of that will be taking time. And also for on 2, people do this. They set y equal to the function here, actually 2x minus 1 by x into 1 minus x, whatever. Okay, and then they solve for x in terms of y to find the values of x. So whether it is possible, if it is possible they say it is on 2, and if it is not possible they say it is not on 2. Okay, but these methods will take much time. Okay, and in an exam like this, a competitive exam, you would not want to waste any time on a single problem, and therefore these methods are not that recommended for competitive exams. Okay, so we'll see what is the trick and how to solve this problem using that trick. Anyway, this f dash x will need, but not at this stage. Okay, f dash x of this will not look nicer. Anyway, so let's see what is the trick and how to solve this problem. Well, so first you can see that this function can be written as this. So 2x minus 1 is x plus x minus 1, and the denominator is x times 1 minus x as it is. This is actually 1 over 1 minus x minus 1 by x, because this is x minus 1 and this is 1 minus x. And this expression is now important. Now if you calculate f dash x, you will see that this is nothing. 1 over 1 minus x is 1 over 1 minus x whole square, because of this minus 1 comes here, but then 1 over x is minus 1 over x square, so minus there plus, and 1 by x derivative of that is minus 1 over x square. Okay, but due to this minus we get plus here. This is so easy to differentiate this function. But you see that this f dash x for any value of x is always strictly positive, right? This is not bigger than equal to, this is strictly bigger than 0, because this expression is always strictly bigger than 0, and this expression is also always strictly bigger than 0. Why? Because these are square terms and not no 0 is possible here, right? So therefore their sum is also strictly positive, and such functions are called strictly increasing. Okay, not called, but you can prove that such functions are strictly increasing, right? So f must be 1 1. Why? Because a function, if it is strictly increasing, must be 1 1. This is an important fact here to note. Okay, so the fact is a strictly increasing function is 1 1. So what is strictly increasing? What is strictly increasing? If x is less than y, then fx must be strictly less than fy, right? So this is strictly increasing function, and that must be 1 1. Why? Because if x is not equal to y, either x is less than y or y is less than x. But if x is less than y, fx is strictly less than fy. Okay, y is strictly less than x, so fy is strictly less than fx. So in either of these cases, fx is not equal to fy. Okay, so if x and y are different, then fx and fy are also different. Therefore, the function is 1 1. That's so easy to prove. So a strictly increasing function is 1 1, and we have seen that f dash x is strictly bigger than 0, and therefore f is strictly increasing, and therefore f must be 1 1. So 1 1 part is done, but the trickiest part is to show that f is 1 2. Okay, so let us come back to our original expression here, fx equal to 1 over 1 minus x minus 1 by x. So you have to prove that this is this function is on to. How to prove this? So as we said earlier, we will not set this to y and then solve for x in terms of y. That is a method, but that method doesn't work here. Okay, rather what we will do here is the following. First of all, the domain is 0 1. Okay, so somewhere it is 0 and somewhere it is 1, right? And 0 1 open, right? So 0 is excluded, so exclude 0, and also 1 is excluded, so exclude 1, right? So this is my domain, and the function is something like this. First you check that this function is continuous. Why? Because this denominator is never 0. Why it is never 0? Because x cannot be 1, x cannot be 0, because they are strictly in between 0 and 1. 0 and 1, they are excluded. So this denominator is never 0, and therefore this function is continuous. It's so easy, and also this is differentiable, as you have seen. So since this is a continuous function, it will be like something like this. Okay, but whether it goes all along till infinity, and whether this goes to minus infinity, if that is the case, then the function must be onto, right? Because it is going beyond any value, any height, and it is going below any value or any depth, right? So it is going to infinity, minus infinity, it is going to plus infinity. If that is so, then the function is onto, right? But to check this, what shall we calculate here? We have to calculate limits, right? So basically limit you have to calculate x going to 0 plus, because this is the only possible direction here, because this part is not in the domain. So x going to 0 minus is not possible. So this direction is the only possible direction. Similarly here, this direction is the only valid direction, right? Because this part is not in the domain, not here, right? So we have to calculate two limits, limit x going to 0 plus fx and limit x going to 1 minus fx. Okay, we have to calculate these values. So to check the behavior of f around 0. Okay, if it is bounded by some value, it is not going beyond anywhere, then the function cannot be onto, right? So suppose if the function is bounded like this, okay, then if we take any bigger value y here, okay, it is never reaching that line, right? So it will not be onto. Anyway, you understand that the logic here, but you have to calculate this limit first. So what is limit x going to 0 fx? So this is fx. Use this expression. Use this expression of fx to calculate these limits, because then this is easier. So x going to 0 plus, you can just put 0 here. There is no problem in this part of the function. So this becomes 1, right? This becomes 1, and then minus x going to 0 plus this. If x going to 0 plus, then the values are very close to 0, but still they are positive, and 1 over positive is positive. So this becomes plus infinity. Okay, so 1 minus plus infinity, which is nothing. If you calculate, because of this minus, it becomes minus infinity, right? Similarly, what is limit x going to 1 minus? 1 minus means the values are very close to 1, but they are never 1. In fact, very close to 1, but they are lesser than 1, right? So if you take x here, which is very close to 1 but less than 1, this 1 minus x term will be very close to 0 but positive, right? And therefore the limit x going to 1 minus fx, so basically for this term you get plus infinity, and for this term there is no problem, you can put x equal to 1, so it will be minus 1. So if you calculate, it is plus infinity. So when x is approaching 0 here, so when x is approaching 0 here, the function is going to minus infinity. So it is going below everything, okay. And when x is very close to 1 here, okay, the function is going to plus infinity, okay. So now if you take any value of y, let's say y equal to c, then you draw that straight line, it will cut somewhere, right? And that is the value of x, that is the value of x, okay. So therefore this function f, because of this fact, okay, the function is onto, because it is going everywhere, it is going everywhere, and the function is continuous, and therefore there is no break. So this function is actually onto, and this solves the problem. Okay, that's all in this video, and I thank you for watching.